So we have introduced the STO basis. The advantage of STO basis, of course, STOs, the Slater type orbitals, are analytical functions, right? And they're simple enough so that the derivatives or integrals in an actual molecular calculation can be evaluated analytically. That's the advantage, right? Otherwise, if you want to use the exact numerical solution for the atomic orbital, you need to do the numerical integration, and that is super expensive. That's simply not affordable. Okay, if you want to use the numerical solution of the atoms at your basis. The disadvantage, of course, the disadvantage is that actually, yes, you can indeed derive the integrals by using the STOs, but the multi-center integrals are very expensive. So I should write down the disadvantage. Disadvantage is that the multi-center integrals are very expensive. Multi-center means, well, you have more than one center. You have more than one nuclei, right? When we study a molecule, we have more than one nuclei. That's multi-center. There's no way to, well, for Slater type orbital, you cannot find a simple way to combine two-centered integral into one center. Right? Otherwise, you can reduce your computational cost. But for Slater type orbital, you cannot do that. Right? And when I say integral, what does that mean? That means the matrix element, right? We talked about the matrix mechanics previously. So your central task is to diagonalize the Hamiltonian, right? Diagonalize the Hamiltonian matrix. So for a molecule, that's the same. You can construct a very huge matrix for your Hamiltonian. And the matrix element, if you remember our previous matrix mechanics, the matrix element, say Hij, is this integral, phi I Ri H phi j Rj. Okay, or if you use dummy index, let's just use R. Let's just use R as a dummy index. For the first electron, if we're doing a single electron theory, then the first electron or second electron, they have the same form, right, essentially. So this is the matrix element. Here, Ij, of course, is the AO, right? This is your approximated AOs, right? This is the matrix element. Of course, you can have single electron integrals. What are the single electron integrals? Well, single electron integrals simply means the kinetic energy, right? Kinetic energy only depends on one electron. It doesn't depend on other electron, right? So phi I R kinetic energy operator, phi -1/2 Laplacian, phi j R. This is the matrix element of the kinetic matrix, kinetic energy matrix, right? So if we consider, say, you have nucleus A, you have nucleus B, you have nucleus C, right? It's a molecule. Then you have multiple electrons. Say, let's consider this electron here. Then you have a vector Ra, right? You can also have Rb, Rc, etc. Right? So now the nuclear electron interaction, Ij nuclear electron interaction, which is this integral, phi I R Za over Ra phi j R, right? This is just the nuclear interaction of the electron that, say, electron R1 with the nucleus A, right? So this is also a single electron integral. But other than single electron integral, you can have two electron integrals. Right? Because you have multiple electrons. For instance, typically VEE, electron-electron interaction, right? Actually, you can have 4 indices. In general, this kind of integral can give you 4 indices. Phi I 1, phi j 2, 1 over R1 2, phi k 1, phi L 2. Right? This integral is over R1 and R2. Right? So this is electron-electron interaction. Right? You can have electron in orbital I, electron 2 in orbital J, electron 1 in orbital K, electron 2 in orbital L. So when you construct a matrix, you will have this kind of matrix element. Okay? So this is definitely a 2 electron integral. Of course, you can consider a multi-center. Right? So again, you have A, B, C, for instance, A, B, C, D, for instance. This is your molecule. Those are the nuclei. So let's consider you have the first electrons here, the second electron here. Then, of course, if you want to talk about the nuclear electron interaction, you can have this vector, right? This vector. And, well, you can also have this vector, right? And for electron 2, you can have this vector, this vector, this vector, and this vector, right? Multiple terms, right? Of course, you can have multiple terms. But you know, this electron, say electron 2, can also be I need to erase these lines, otherwise you cannot see anything I'm drawing. Okay. So multi-center really means the integral that involves an electron with, say, 2 centers, with 2 nuclei. Or, for instance, electron 1 with 2 nuclei. It doesn't have to be BD, it could be AB or AC, etc. Right? You can have this kind of integral. So this will be phi I R A1. That is the vector that's connecting nucleus A and electron 1. And phi J are B2. Right? This is the vector that is connecting the nucleus B with electron 2. And by using the basis phi J. And the interaction between the electrons, of course, is 1 over R1, 2, right? So phi K are C1, phi L are D2, for instance. I'm just writing an example, right? Again, this integral is over dr1 and dr2. This is multi-center because it involves multiple nuclei, right? So all of these integrals in the future, you will need to, well, you don't need to, but I will say we will introduce or we will encounter all of these integrals when we talk about a more high-level approximation of the many-body system, right? Of course, in a non-interacting single particle picture, you don't have 1 over R1, 2, right, in the Hamiltonian. So in that case, you can say, okay, you may think okay, you don't need to evaluate this integral. That's not true, actually, because what I just said is, well, the total energy is approximately equal to the summation of the single particle energy, but it's not entirely true. You also need to consider the Coulomb repulsion between two electrons occupied on two different orbitals, right? Two different spin orbitals. And you have the so-called exchange interaction between two electrons. And when you try to evaluate these interactions, you need to calculate these integrals. All right. All of these integrals are called the molecular integrals. We will not actually talk a lot about the molecular integrals in this course because it's somewhat a specialized topic. But I think it's good for you to know that you will be using these integrals in an actual molecular quantum mechanical calculation. Okay, you personally do not have to evaluate these integrals, but by choosing appropriate basis, you need to do that by yourself, right? You need to choose a basis, and then the computer can calculate the integrals for you, calculate the matrix element for you, right? So what you're doing is you're choosing a basis and use the basis function to calculate these integrals. So if you're doing a Slater type orbital, you can of course, you can evaluate these integrals. It's just that when you do a multi-center integral, when you consider multiple nuclei, it's not very cheap. The calculation is going to be expensive because you need to do multiple centers. So another way to do this is, or another type of function is called a Gaussian function, or Gaussian type orbitals. This type of the orbitals actually, I think, are the most popular orbitals or most popular basis you will use in actual molecular quantum calculation, right? The reason that people introduce this set of orbitals is because it's very easy to evaluate the molecular integrals. And for the Gaussian type orbitals, a multi-center integral can be reduced to a single center integral. So if you have, say, 4 center, you can first reduce the 2 center into 1 center, and another 2 center into 1 center. And now you have overall a 2 center integral. Then you can further reduce this 2 center integral into a single center integral. So you can enormously reduce your computational cost. That is the advantage of the Gaussian type function. So the first advantage is it's easy to evaluate molecular integrals. Actually, this set of Gaussian function is introduced in 1950 by Boyce. And of course, analytical results are valuable. Actually, they are simply algebraic expressions. I should say analytical integrals are available, are simply algebraic expressions. So actually, all of those expressions for the Gaussian type functions are already tabulated. They are tabulated and stored in computer softwares. So it's really, you just, whenever you need it, you just call this subroutine. Then you have this value, right? So it's quite easy to do. You just insert the particular parameter that you introduced in the function, in the basic function. That's it. Then you can very quickly get the result for these integrals. Okay, and the third, I think, the most important one is that a multi-center, for a Gaussian type orbital, a multi-center integral can be eventually reduced to a single center integral. This is, of course, a enormously important contribution, right? This is very important in terms of cutting the computational cost. So next, I will talk about the actual functional form of the Gaussian type orbital. But in this lecture, I will not talk about how to derive this property, how to derive this multi-center integral can be reduced to a single center integral. I think I leave it in your homework, so you can derive it by yourself. It's not hard. It's just, actually, it's a good practice on your vectors and the trigonometry. And after you figure that out, then, because the Gaussian function is simple exponential function, and you can just do a simple multiplication, and you will find out that indeed a multi-center integral can be reduced to a single center integral. All right. But of course, if you have any trouble in terms of actually proving this property, then you can ask me. Okay. So let's consider we have a nuclei. We have a nucleus here, and an electron here, and we have a vector RA, and let's put the origin of our coordinate here. So in general, if you're doing a molecule, the origin of the coordinate is not on a particular nucleus. So the position of this nucleus is RA. And the position of this electron is small r. Okay, so RA is, of course, r minus the position of the nucleus. Okay, this is just the notation, because I need to use this notation in defining the Gaussian type orbital. There are actually two ways to define the Gaussian type orbital. The first way is to define the so-called spherical Gaussian type orbital. GTO is an abbreviation for Gaussian type orbital. So the radial part, of course, again, it's the radial part that we need to approximate. The angular part is just the exact spherical harmonics. NL GTO, which depends on a parameter alpha, and it is a function of RA. RA here, RA is the magnitude of the RA vector. So this is basically the function form. I will not write down a bunch of coefficients, because the coefficients sometimes, because we require the function to be normalized. So of course you will have a normalization constant. And sometimes normalization constant is very complicated. So I will only write down the essential part of the Gaussian type function. So as you can see here, it's exponential negative alpha times RA squared. This is a Gaussian function. And in front of it, you have several other terms, okay? So if you let n be equal to L plus 1, then this Gaussian function can be further written as square root 2 alpha RA to the L's power exponential negative alpha RA squared. Okay. So this is one of the definition. This is the so-called spherical definition because you are using R as the variable here. Another definition, which is also very commonly used, is called the Cartesian definition. The Cartesian Gaussian type orbital. A Cartesian type GTO depends on a parameter and XA, YA, and ZA. Right? Because, well, here we have RA, right? Here we have RA. Then in terms of the Cartesian coordinate, of course, you have XA, YA, ZA. And this is a simple, this can be written as a simple product of the XA part times the YA part times the ZA part. Well, from this definition, you immediately notice that it's really not the exact solution, right? Because for the exact solution, if for instance, take a hydrogen wave function, if you express your wave function in terms of x, y, z, there's no way to separate this x, y, z function to a product of three terms, and each term only depends on x or y or z. There's no way to do this for the exact hydrogen atom, right? But for the Cartesian Gaussian type orbital, it is defined to have this property, okay? So the GTO alpha XA is essentially XA to the L's power exponential negative alpha XA squared. This actually, if you look at this, the spherical definition here, you see if you write RA as XA square root times, well, if you write RA as XA squared plus YA squared plus ZA squared square root, then this term here cannot be separated. But if you write RA squared in the exponential term, XA squared plus YA squared plus ZA squared, you can separate this exponential term into the product of the three terms, exponential negative alpha times XA squared, exponential negative alpha times XB squared, YA squared, and another term is exponential negative alpha times ZA squared, right? So based on this separation of the exponential term, which is really the core of the Gaussian function, people propose this Cartesian type. So L GTO for the Y part is YA M. They use a different index here actually. So this is exponential negative alpha YA squared. Our GTO, let's use another index, say N alpha ZA, the Z part is ZA N exponential negative alpha ZA squared. All right. So this is just the definition of the Gaussian type of the Cartesian Gaussian type orbital, right? So let's examine these functions. If let's consider, say, L is equal to M is equal to N is equal to 0. If L is equal to M is equal to 0, this is conventionally called the 1s type GTO. This is just a name. It has actually nothing to do with the exact solution of hydrogen, okay? So N is equal to 1, L is equal to M is equal to 0 is usually called 2PZ type of the GTO. M is equal to 1, L is equal to N is equal to 0. This is called 2PY type of the GTO. It has nothing to do with the exact solution and the exact quantum number. Here, N, L, M are just the three, I will say, three indices, or you can say three parameters to specify the type of GTO. You just call this 1s, 2px, 2py, that's it, okay? This is called 2px type. So sometimes when you read the literature, for instance, if you find other people are talking about, I'm using a 2py orbital, I'm adding an additional S-type orbital, a Gaussian type orbital in my basis. It doesn't mean he's adding a physical solution of the hydrogen atom or hydrogenic system. No, it means he means actually is adding this mathematical function with a particular combination of NLM in his basis. That's what he means, okay? I should write it here. This names and NLM here have nothing to do with the solutions of the hydrogenic system. Okay, they are purely mathematical functions. They are purely mathematical functions. Constructed for practical calculation. All right. Okay. So similarly, as what we did in STO, you can use a combination of Gaussian type orbital to actually approximate the exact solution of the many electron atom, right? Approximated you have many terms. How many terms do you want to use is your choice. The M prime, L prime, R M prime, L prime, GTO, RA, alpha M prime, L prime. So this and this are fitting parameters. Okay, actually many physical chemists have already done this type of fitting for you. They have created a series of basis set that you can use. Different basis set have different size, or you can say have different basis set have different K value, have different size, okay? So you can pick the one that you think that you can afford for your current molecular quantum mechanical calculation. All right. So usually what people did is actually, they do not, when they do this linear combination of Gaussian type orbital, they do not fit the exact numerical solution of the many electron system, because they have, at that time, they have already did a lot of work on Slater type orbital. So, so they have developed a set of high quality Slater type orbitals. So actually, when they later they do this GTOs, Gaussian type orbitals, what they do is they actually try to fit the STO. Right? The STOs at that time at say 1950 is already available actually for all the important atoms. So since they have already know the analytical expression, which is really a linear combination of the elementary Slater type orbitals, then they just use this analytical function as the target to determine the parameters here, right? So you can express the STO as a linear combination of GTOs. Okay, that's what they did historically. So this is called STO KG basis. Well, because the STO orbital is approximated by K, a linear combination of K Gaussians. Each Gaussian here is actually called a primitive Gaussian. Each term here is called a primitive Gaussian function. So of course you have K terms, right? You have K terms here. All right. So actually this is proposed by John Popo. 1969, the Popo basis set. Okay, it's a very famous set of basis set, and even nowadays people are frequently using Popo's basis set. But of course, people are not using STO-KG basis set because it's not a particularly high quality basis set. Popo has developed a series of basis sets that are widely used in molecular quantum mechanical calculations. But it's just that at that time, the first effort is to try to approximate STO, which is already known in the 1950. So try to approximate STO by using a linear combination of K Gaussian functions. Okay, but this is STO-KG is actually rarely used in modern molecular quantum mechanical calculations, because in order to get a very high quality, you need to use a very large number of K. This is not very practical. So you have other ways to design your functions. For instance, you can further introduce some flexibilities. For instance, there is a type so-called split valence basis. For instance, the notation could be, in the literature, sometimes people use the notation 631G or 311G, or this type. I should write multiple, so multiple ones. 31G or 6311G, etc. G, of course, represents the Gaussian function. And what is split valence? Actually, it means each core So for instance, let's consider just 6311G. Let's consider this. This means each core electron orbital is represented by 6 primitive Gaussian type orbitals. Okay, it's a linear combination of 6 primitive Gaussian type orbitals. The coefficients, of course, are obtained by fitting. And these are actually called the core contracted Gaussian type orbitals. Okay. And each valence electron orbital, so you have core electron, right? And you also have valence electron. Each valence electron orbital is represented by 3 sets of orbitals. Here, this 6 means for the core electron, you have 6 primitive. And you have 3 numbers here, right? 3, 1, 1. There are 3 numbers. That means for each valence electron, you actually have 3 sets of the Gaussian orbitals. So the first set, set 1, is that it includes 3 primitive Gaussian type orbitals. Set 2, it includes 1 single primitive Gaussian type orbital. Set 3, it includes 1 primitive Gaussian type orbital. And therefore, you have the notation 311 here. This is 311. This is notation. Okay. You can construct this set of orbital, which is very flexible. Actually, that's why this kind of orbital 6311G is still actually very popular in modern molecular quantum mechanical calculation. The parameters, the coefficient for the linear combination, and the exponent in the Gaussian function. So the alpha parameter here. So this alpha parameter, right? This is in the exponential term. This exponent is also optimized by fitting. Okay. But actually, when they develop this basis, the fitting is not against the actual atomic orbital. It's against a series. You first use this set basis to do the so-called Hartree-Fock calculation, and then you fit these parameters against the experimental, for instance, experimental atomic ionization potential or atomization energy. Those are experimental observables about the energies. Okay. So you can also have the so-called diffuse function. For instance, I just give you one example. In the literature, if you see this symbol 6311 plus G, this plus sign means diffuse function. Diffuse really means what? Because for Gaussian type orbital, you have this alpha parameter, which is on the exponential term. That means the Gaussian type orbitals with really a small exponent alpha. So that if you see the Gaussian type orbital, so let's say this is alpha 1, okay? This is a Gaussian type orbital. If you use a small alpha, because it's exponential negative alpha r squared. Then if you use a small alpha, you will have something like this. Okay? This is a small alpha. So it's decaying slowly, a little bit slowly, right? If you have a small alpha. That means the electrons are sort of delocalized, right? The probability distribution is kind of delocalized, right? The electrons can be extended to further range, right? That's the diffuse mean, right? For instance, this is important when you do anions, or say the pi conjugated system. This is very useful. Very often you want to add diffuse functions. Another type of the function is called polarization function. Polarization function can add additional flexibility for describing bounding. For instance, sometimes, I should say, for instance, sometimes in the literature, you see this notation. For instance, 6311G dp, or another notation is 6311 G star star. This two symbol means the same thing. This parenthesis dp means the additional flexibility. These are the polarization function. It really means add p orbitals for hydrogen and add d orbitals for lithium to neon. This means you add additional p orbitals for hydrogen and add d orbitals for lithium to neon. So for hydrogen, usually we'll only talk about the s electron, but you can add more flexibility. You add p orbital on hydrogen. You add a d orbital on the first row, actually. From lithium to neon, it's usually called the first row, but actually on the periodic table, it's second row, but usually people like to call it first row. First row atom means lithium to neon. Okay. And again, this so-called p orbital and d orbital are just mathematical construction of the Gaussian type orbital. Okay. Do not view them as the physical orbitals, although they can be used to capture some physical effect. You can provide more flexibility for bounding. But I think you should really view them as purely mathematical functions.